Hi, everyone, and welcome to Lecture 13, Part 3, the last of our graphing lectures. And we're going to continue from last time. I apologize, I was working under a handicap called temporary insanity. But we were working on the graph of this function. And our model is going to be, or our basic repertoire function that we're going to use for reference in comparison to this is f of x equals x squared. So let's draw that. This is our initial reference function. And now the trick here, when we have both a horizontal stretching and a horizontal shift, essentially we handle this the same way that we handle a function that has a vertical stretching and a vertical shift. We do the stretching first. So as our next function for comparison, we're going to look at f of x equals quantity 1/2 x squared. That's going to be our function of reference. And let me write this up higher so that I don't deprive myself of space that I'm going to need later on. What does this do? Stretches everything out by a factor of 2. So these are our reference points. And horizontally, everything stretches out with reference to the origin by a factor of 2 each way. The x-coordinate here is 1. So the x-coordinate here of the corresponding part on our graph is 2. The x-coordinate here is -1. So the x-coordinate of the corresponding part over here is -2. Cool. Now we have one more thing to incorporate, and that's the horizontal shift. And now remember, f of x plus c is a shift left. F of x minus c is a shift to the right. So we're shifting everything to the right 1 unit. Which means we're going to take this graph, pick it up, and move the whole thing 1 unit to the right. So this point that lies on the origin is going to be 1 unit to the right. It's going to lie at 1, 0. This point that lies at x equal 2, y equal 1, we shift it 1 unit to the right. So it's now going to be nice if I could count, wouldn't it? We take this point that's at x equal 2, we shift it 1 unit to the right. The corresponding point on this graph is x equal 3, y equal 1. At this point, at x equal 2, y equal 1, we shift it 1 unit to the right, so it's going to be at x equal negative 1. And here we have the skeleton that we're going to hang our graph on. That's our graph. Now, don't take my word for it. Please don't take my word for it. But let's just check and make sure that it works. And we'll check out these key points. X equal 3. If we take x equal 3 and plug it into the equation, we should get the y coordinate 1. Do we get that? Let's see. Take 3 and put it in for x. We have 3 minus 1 is 2. Times 1/2 is 1. We have 1 and we square it and we get 1. That looks pretty good. Let's make double sure. Let's take the x coordinate here, x equal 1. If we plug it into this function, we should get the y coordinate 0. Do we get that? Take x equal 1, and we have x minus 1 is 0. We multiply it by a half. The half times 0 is still 0. And then we take 0 and square it, we still get 0. Things are looking good. Now let's look at the last key point here, x equal negative 1. If we take x equal negative 1 and plug it into our function for x, we should get the y coordinate, which is positive 1. Is that what we get? Let's see. Negative 1 minus 1 is negative 2. Negative 2 times a half is negative 1. We take negative 1 and square it, we get positive 1, which is the y coordinate. Okay. This is what the graph of f of x equals 1/2 x minus 1 squared looks like. Now let's do some more examples. Holy moly, what on earth have I done here? You know, it kind of looks like this 3 and that 1/3 will sort of cancel each other out. But I'm betting that it doesn't. The first thing that I'm going to do is I'm going to graph that basic function from my repertoire of functions that most closely resembles this. And that's going to be x cubed. I'm going to graph that function. And we have our old friends, negative 1, 1, and 0, that we use for reference. And when x is 1, x cubed is 1. When x is negative 1, x cubed is negative 1. And when x is 0, x cubed is 0. And we have the graph of x cubed. Next, I'm going to work with the 1/3 because it's inside the parentheses. And notice something. I'm taking 1/3 x in parentheses and then I'm cubing it. The 3 here is on the outside of the parentheses. So they do different things. The 1/3 is on the inside of the parentheses. I multiply x by 1/3 before I cube it. So this thing is going to be a horizontal stretching. This thing is on the outside of the parentheses. I cube my x and everything else, and then I multiply it by 3. So that's going to be a vertical stretching. First thing I'm going to look at, f of x equals 1/3 x cubed. This is a horizontal stretching. And it's going to stretch everything horizontally by 1 over whatever this thing is. We're going to stretch things by a factor of 1 over whatever this thing is. So 1 over 1/3 is 3. Everything's going to be stretched out horizontally by a factor of 3. So 1, 2, 3. -1, -2, -3. I'm going to take the x coordinate here and multiply it by 3. I'm going to take the x coordinate here and multiply it by 3. I'm going to take the x coordinate here and multiply it by 3. In this case, I still get 0. So now this is what my graph is looking like. Holy moly. Now the next thing that I have to do is account for the vertical stretching. And this is vertical because it's 3 times something cubed. We're doing the cubing first, and then we're multiplying by 3. The 3 is not inside the parentheses here. It's, if we had the 3 inside like this, then it would be horizontal. But we have the 3 outside the parentheses, it's going to be vertical. So I take this graph, this is a vertical stretch. So I'm going to take this point and multiply the y coordinate 3 by a factor of 3. So this point becomes 3, 3 on the new graph. Let's look at this point. I take the y coordinate and I multiply it by 3. Well, 3 times 0 is still 0. So this point remains the same on the new graph. And now I take this point, I multiply the y coordinate by 3. So the corresponding part on the new graph is going to be -3, -3. I took this point, stretched the y coordinate by a factor of 3 to get the corresponding point on the new graph. And I flesh out the skeleton, and there we have it. Now at this point we might be wondering, did this really change the original graph? Because on the original graph we have points 1, 1 and -1, -1. And on this graph we have points 3, 3 and -3, -3. And we might think, isn't this really the same graph as this? And the answer is no. If it were the same graph, then this point 1, 1 would be a point on the new graph. And it's not. Here's the point 1, 1. It's not on the new graph. As a matter of fact, what is the y coordinate? When x is 1, what's the y coordinate? 1/3 x cubed is 1/27 x cubed. We multiply that by 3 and we get 1/9 x cubed. Holy moly. When x is 1, y is 1/9. Okay? So this is not the same graph as the original. We might look at it and say, well, we got 3, 3 here and 1, 1 here. We got -3, -3 here and 1, 1 here. It's the same graph, isn't it? No. The fact that we have points on this graph whose x and y coordinates are the same doesn't mean that it's the same as the original graph. Not the same at all. And before I talk so much that I forget what my objective is, let's remember that we haven't finished graphing this function. So we've got one more thing to do. And I'm going to move this up a little bit. I'm taking the graph of this function and I'm adding 2 to the y coordinate of every point on this graph. 3 times 1/3 x cubed is my y coordinate here. To get my y coordinate on this graph, I'm taking the y coordinate of this graph and I'm adding 2 to it. This is a vertical shift up. So every point on this graph just gets shifted up 2 units. This point 3, 3, it's going to get jacked up 2 units. This point 0, 0, it's going to get jacked up 2 units. Let's start with this. The origin gets moved up 2 units, so it's going to wind up here. Here's my function. Whoops, whoops, whoops. point -3 gets jacked up 2 units, so the y coordinate will be -1. Oh, crud. And this point, its y coordinate is 3. It's going to get moved up 2 units. The y coordinate will be 5. The graph will be shaped exactly the same way. It's just going to be lifted up 2 units. Voila. This is the graph. F of x equals 3 times quantity 1/3 x cubed plus 2. Let's do another. Holy moly. We're just getting more complicated all the time. Quantity. 2 times quantity x plus 2, whole thing squared minus 3. Well, exactly what this does, we'll worry about step by step. I see something squared here, so the basic function from my repertoire of basic functions that I'm going to use to pattern this after is going to be f of x equal x squared. So I'll draw a graph of that. F of x equals x squared. And I got my old friends, -1, 0, and +1 with me. And when x is 1, x squared is 1. When x is -1, x squared is +1. And when x is 0, x squared is 0. So, bingo, there's my graph. Now, believe it or not, I'm going to let this alone until later. My horizontal and vertical shifts, I'm going to worry about those last. What I'm going to do next is worry about any stretching, vertically or horizontally. And let's see, what does this do? Horizontal stretch or compression? I'll use as my reference the function f of x equals 2x squared. Horizontal stretch by a factor of 1 over whatever this thing is. So it's going to be a stretch by a factor of 1/2. In other words, it's not really going to stretch it at all. It's going to compress it. Everything is going to be only half of its original distance from the origin. So let's see how that plays out when we graph. This point has x coordinate of 1. The corresponding point over here is going to be 1/2 the x coordinate here. Now this point has x coordinate 0. The x coordinate of the corresponding point over here will have an x coordinate that is 1/2 the x coordinate here. Well, 1/2 times 0 is 0. That point doesn't move. And this point, the x coordinate here will have as its corresponding point on this graph an x coordinate that's 1/2 this x coordinate. 1/2 -1 is -1/2. Okay, there are our points. That's the new graph. This graph has been compressed horizontally. The x coordinate, look at this point. X coordinate is -1. The corresponding point on the new graph has x coordinate -1/2. It's been pushed toward the origin. This point on the original has x coordinate of 1. The corresponding point on the new graph has x coordinate 1/2. This point has been pushed toward the origin. It's only 1/2 of a unit away from the y-axis now. Now I guess I'll look at the horizontal shift. Technically, I think I could do either one here, but I'm going to look at the horizontal shift. Whoops. Inside the parentheses, we're adding 2 to x. This is horizontal shift. And if we have a positive sign here, it's a shift to the left, exactly the opposite of what we think it should be. So to get the graph of this function, we're going to take the graph of this function and move it to the left. And let's see, how far to the left are we going to move it? Holy moly, 2 units. Yikes, yikes, yikes. And I think I better put my y-axis over here. No, I think I better put my y-axis somewhere over here in the Atlantic Ocean. My goodness. Okay. I think I can live with this. You know, I guess before I started drawing this graph, I should have taken this point and this point and just figured out where the x coordinates went. If I take this x coordinate and go 2 units to the left, let's see, -1/2 minus 2, that's -5/2. I could have saved myself a lot of trouble if I had just done that to start with. Well, now that I'm talking about this point, if I take this point and shift it 2 units to the left, I'm subtracting 2 units from this guy. -1/2 minus 2 is -5/2. So this is a point on my graph. Now this point, I have to shift this point 2 units to the left. So that means I take the x coordinate here, which is 0, and I subtract 2 units. That's going to put me right here. -2, 0. And let me get this out of them. No, that's okay. -2, 0, that looks good right there. This point, if I move that 2 units to the left, I take 1/2 and I subtract 2. That's going to give me -3/2. Okay, there are my points. Yeah. Yeah. Oh, look at this. Here's my origin all the way over here. Our graph isn't anywhere close to the origin at this point. Well, that's okay. Sometimes the graph of a function isn't close to the origin. Everything looks good. All we have to do now is account for our vertical shift. One last item of business. This is what we wanted to draw the graph of. This is the thing that we graphed most recently. The only thing we have to do to the graph of this function to get the graph of that function is account for the vertical shift. And this thing is a vertical shift down 3 units. So we take this son of a gun, every point on this graph, we just move it down 3 units. So, my goodness, what's that going to do to our graph? Whoops, I should have known better. Draw my origin over here because that's where my origin is in this graph. The y-axis is way the heck over there. And let's see now. Maybe I should figure out where these points are going to go. That's what I should have done when I graphed this last time. And eventually I did that, but it took me a couple of tries before I realized, wait a minute, I'm not giving myself enough room on the graph. So let me figure out where this point goes. The x coordinate's going to stay the same, but we're shifting it down 3 units. So we're going to subtract 3 from the y coordinate here. So we got a -3 right here. Holy moly. -3, -2, -1, 0. Okay, here's my origin. Son of a gun. And I'm going to go 1/2, -1, -3/2, -2, -5/2. And I'm going to run out of blackboard, but hey, what can I do? Subtract 3 from this point, the y coordinate, I get -2. Nope. I get -2x, -3y. Son of a gun. I take this point and I subtract 3 from the y coordinate, so that puts me at y equal 2. X equal -5/2, y equal 2. And I do the same with this point, -3/2 x. And I subtract 3 from the y coordinate, so that puts me at -2. And if I really cared, I'd try to find the x-intercepts here. I might even try to find the y-intercept, but that may be up here somewhere. Okay, we'll see some exercises like this on our homework, so let's do them. Compared to what we've been doing, these ought to be a snap. Write the definition of the function whose graph is formed by taking the graph y equals x and shifting the graph to the right 3 units. Okay. So we start like this. F of x equals absolute value of x. Now, if we're shifting to the right, that means we're going to have x minus something, right? F of x equals x plus c. That's a shift left. F of x equals x minus c. That's a shift to the right. So I guess our new function, we're going to take this baby and shift it 3 units to the right. That means we have a minus sign here. Ah, son of a gun, that was a toughie, wasn't it? Before I go on to another exercise, I just realized what this was supposed to say. Write the definition of the function whose graph is formed by taking the graph of y equals absolute value of x, but is shifted to the right 3 units. That's what the example that we just did was supposed to say. So let's see, what did we do? We took f of x equals x from our repertoire of basic functions, and we shift right. And we mentioned that f of x equals x plus c is a shift left. C units, f of x equals x minus c is a shift to the right. And we want to shift right by 3 units. So that gave us f of x equals absolute value of x minus 3. Okay. Now we did the exercise correctly. It's just that I didn't realize what I needed to do to correct the wording up here. Taking the graph of y equals absolute value of x and then shifting to the right 3 units. Okay. I think this time I really do have the wording right. Write the definition of the function whose graph is formed by 1, taking the graph of y equals cube root of x, and 2, shifting the graph left 3 units. So here's what we do. We take our reference function, f of x equals cube root of x, and remember, if we have f of x equals, in parentheses, x plus c, garbage, the plus c indicates a shift to the left. Which is what we want to do in this case. We want to shift left 3 units. So we take this function, and just inside the square root, we have x minus 3. And since everything under the cube root is considered to be together, we don't need the parentheses, but if we want to put them in there, that's fine. So this is a shift. Wait a minute. Shift left 3 units. That should be a plus sign, shouldn't it? Hold the phone. Okay. Cube root of x plus 3. There we go. That's a shift to the left 3 units. Another one like this. Write the definition of the function whose graph is formed by 1, taking the graph of y equals square root of x, and then 2, shifting the graph up 2 units. So this is a vertical shift by 2 units. And remember, with the vertical shifts, what we expect to happen does happen. We start with our basic repertoire function, f of x equals square root of x. And to get a vertical shift upward, we just add the amount of the vertical shift. To shift it up 2 units, just add 2. The only precaution is we're adding 2 to the entire function. F of x and square root of x, f of x and y are synonymous. So if we want to shift this graph up vertically 2 units, we need to add 2 to the y coordinate of every point on this graph. So we take the y coordinate of every point on this graph, and that's square root of x, and we add 2 to it. The 2 does not go inside the square root. That would make it a horizontal shift. Write the definition of the function whose graph is performed by 1, taking the graph of y equal x cubed, and shifting the graph down 1 unit. Down, that's a vertical shift. So we go with our basic repertoire function. F of x equals x cubed. And now we're going to shift it vertically down. So we take the y-coordinate of every point in the original function, and f of x and y are the same thing, remember that. So if f of x equals x cubed, then x cubed is the y-coordinate. And to shift it down 1 unit, we subtract 1 from that y unit. There's our vertical shift down. Now let's do one more like this. Write the definition of the function whose graph is formed by 1, taking the graph of y equals x cubed, and 2, revolving it about the x-axis. Now in our book, instead of saying revolving it, they may say reflecting it. When you see the word reflecting there, that's what they're talking about. So we start with our model function, f of x equals x cubed. And to take an entire graph and revolve it about the x-axis, what do? Multiply it by -1. That takes the original graph and flips it about the x-axis. So here's f of x equals x cubed. And to get the graph of f of x equal -x cubed, we take this graph and revolve it about the x-axis, which means this is what we're going to get. This part gets revolved above the x-axis. This part gets revolved below the x-axis. And voila, we have f of x equals -x cubed. I'm not sure we've actually seen one like this before, so maybe we should do it now. And it has to do with revolving something about the y-axis. Write the definition of the function whose graph is formed by taking the graph of y equals x cubed and revolving it or reflecting it about the y-axis. If we revolve about the x-axis, if we have the function y equals f of x, to revolve it about the x-axis, this is what we do. We take the y-coordinate, which is f of x, and we multiply that y-coordinate by -1. We revolve it about the x-axis. To revolve it about the y-axis, I don't know if we talked about this or not, but here's what we do. To revolve it about the y-axis, we don't multiply the y-coordinate by -1. We multiply the x-coordinate by -1, which means the negative sign goes in here. Note the distinction between these two things. To revolve it about the x-axis, we take the entire function and multiply it by -1. To revolve about the y-axis, we take x inside the function and multiply it by -1. And we're going to revolve this baby about the y-axis. That's what it says. So we have f of x equals x cubed. And to revolve it about the y-axis, we want f of -x. And that's going to be -x quantity cubed. Now, let's do another example of this, because this is somewhat ambiguous. And here's our new example. Well, take this example, reflect it about the y-axis. Here's our initial function. And to reflect it about the y-axis, we take x and we change it to -x before we plug it into the cubing function. This one's going to be challenging. This one really is. It's like, It's like the exercises in the group that contains number 67 in our homework. So let's pay careful attention to how we do this. But we're given this function, and it says graph the function by 1, completing the square, and then using known graphing techniques. So I think we want to complete the square here just so that we can write it in the form of x plus or minus garbage quantity squared plus a vertical shift. I think that's what they want. So let's complete the square. Now, if this is already a perfect square, then the constant term will be equal to 1/2 the coefficient of x quantity squared. The coefficient of x is -6. If we take half of that, we get -3. And when we square it, we get 9. Oops, that's not what this is. So this is not in the form of a perfect square. We're going to use completing the square technique to get this in the form of a perfect square. And let's see, how will I do this? I'll take the constant term and separate it from the rest of the expression. And I'm going to take the expression inside these braces. This is the expression whose square I'm going to complete. And here's what I do. I take 1/2 the coefficient of x and I square it. So here I go. I take the coefficient of x, which is -6. I take 1/2 of that and I square it. There's only one problem. I've just added this amount to the right side of the equation. See, we still have f of x on the left. And I've taken this amount just very arbitrarily and whimsically. I've added this much to the right side of the equation. I can't do that. To atone for my sin, I'm going to take this thing that I added to the right side of the equation and I'm going to subtract it right back. So I added this thing, I'm going to subtract it right back. So the net effect is I added this thing, I subtracted this thing. The net effect is that I've added 0 to the right side. So I'm good. Now I'm going to simplify a little bit. I'm going to simplify a little bit. And I'm going to write the expression in these braces as a perfect square. And here's what I'm going to get. I'm going to get x plus or minus something squared. Well, what's it going to be? It's going to be this thing right here along with its sign, plus or minus. So this thing in the braces is equal to x minus 3 quantity squared. And here I have 5 minus a -3 squared, that's -9. So I have x minus 3 quantity squared minus 4. Actually, I think that helps me out quite a bit. It may not look like I've accomplished anything here, but I think I have. Watch and see what happens. Okay, here's where we are. I used completing the square to transform this equation into this equation. They are one and the same equation. The right-hand side is just in a different form here, that's all. But I look at this thing, in parentheses I have x minus 3 quantity squared, and I say to myself, aha, horizontal shift right 3 units. So let's see how I graph this. F of x equal x squared. F equal x squared looks like this. Then I do my first alteration. F of x F of x equals x minus 3 squared. And as we said, this is a horizontal shift to the right 3 units. So I'm going to pick this graph up and move it 3 units to the right. The x-coordinate here is -1. If I shift it 3 units to the right, I'm adding 3 units to this x-coordinate. It'll be +2. And this coordinate, this point rather, is the origin. If I move it 3 units to the right, I add 3 units to this x-coordinate. That'll make it x equal 3. And this coordinate, I'm going to move it 3 units to the right, which means I'm going to increase this x-coordinate by 3 units. Add 3 units to this x-coordinate, I get 4. And this is my new graph. I took this graph and moved it 3 units to the right. And from this graph, I want to get this baby. Well, what is this guy? Vertical shift down 4 units. I'm going to take this graph and just move everything down 4 units. This point, which lays on the x-axis, gets moved down 4 points from 3, 0 to 3, -4. This point gets moved down 3 units. No, I'm sorry, it gets moved down 4 units. Subtract 4 units from y equal 1, we get y equal -3. And similarly, this point gets moved down 4 units. Subtract 4 from the y coordinate, we get y equal -3. I've got the bottom of the graph. Now, the instructions also said we could use other graphing techniques. What would I want to know here? I might want to know where this graph crosses the x-axis. And I might want to know where it crosses the y-axis. when x equals 0, the graph crosses the y-axis. I can use either this equation or this equation to find that. And what this says is, when x is 0, y is 0 squared minus 0 plus 5. When x is 0, y is 5. Holy Moses. Holy moly. 1, 2, 3, 4, 5. That's a point on the graph. Yikes, yikes, yikes. The y-intercept. So x equals 0, y equals 5. Son of a gun. Well, what about the x-intercepts? That happens when y equals 0, right? This was the y-intercept. The x-intercept, let's see. Graph crosses the x-axis at y equals 0. So that's the x-intercept. This equation's probably going to be the best one to use. This is y. F of x is y, so we're letting y equal 0. Y equals 0, which equals x squared minus 6x plus 5. And does this factor? Well, maybe it does factor. Let's see. We are so lucky. I thought I was going to have to use the quadratic formula to factor that, but no, this thing factors. Let's see. No. X minus 1 and x minus 5. Does that work? Let's see. Negative 1 times negative 5 is positive 5. That looks good. Negative x minus 5x is negative 6x. Okay, beautiful. The product of these two things equals 0, so either x minus 1 equals 0 or x minus 5 equals 0. If this is true, that means x equals 1 or x equals 5. Those are the x-intercepts. One, 0, and 5, 0. And there is our graph. It shows the intercepts. It shows the vertex. I don't think we can do much better than that.